In this paper, we are going to speak about applying compiling technique in DTD conversion. This work is done in collaboration between the Lebanese University, the USEC University, and the Cincinnati University School of Information Technology. Let us speak about our objective. To do the conversion, we think about something new which is different from other techniques proposed in the literature. We want to apply compiling techniques. We first generate the set of DTD by a context-free grammar. Next, we want to express each DTD by defined attributes over the grammar G DTD. We will process model conversion by two steps. Rewrite the source DTD into intermediate model called DTD XML. Develop the conversion by using XSLT style sheet. We have a DTD. We write productions over the DTD. We obtain the grammar G DTD. We define attributes and semantic equation over the production of GTDD. We obtain DTD XML model. We use XSLT to convert the intermediate model to any other model, such as XML schema and database model. In the literature, some research papers try to write a mapping algorithm to convert DTDs to database schema. Example, the algorithm converts composed element to class and scalar element to attribute. Then each class is converted into tables and the attributes of the class are converted into fields. In our research, we will try to first convert the DTD model into an intermediate model and then develop the conversion by using XSLT to obtain, as example, database model or PDF files. Let us now define the notion of a grammar. A grammar is composed from a set of terminal symbol sigma called the alphabet of the language, a set of non-terminal symbol n to generate words of the language, a starting symbol s and the production used to define the language and how to generate words, a set A that is composed from two sets of attributes, a set of synthesized attributes AS that are computed from bottom to top and from left to right, a set of inherited attributes AH computed from top to bottom and from left to right. We have also a set E of semantic equations computed from each production. For the set of synthesized attributes, the computation is from bottom to top and from left to right using the function fs, where s of x0 is equal fs applied to s1 x1, sn xn, and h of x0. For inherited attributes, the computation is from top to bottom and from left to right using the function fh, where hj of xj is equal fh applied to h0 x0, s1 x1 till si xi, where I less than j. Example, given the following grammar for a given programming language, a program is composed from a main followed by declarations and statements. Each declaration defines an integer variable, and we can have several declarations. Each statement defines a value assigned to an integer. Based on these productions, we can generate the following program. The problem is how to find the used and not defined variables. By applying the grammar productions on the program, we obtain the following derivation tree. To solve the problem of used and undeclared variables, we use the following attributes. N is a synthesized attribute to count the number of lines used in the non-terminal declarations. N prime is an inherited attribute used in the non-terminal declaration and the statement to count the number of lines. D prime is an inherited attribute used in the non-terminal declarations and the statements to store declared variables. U and D is a synthesized attribute used in the non-terminal statements to store undeclared variables with line numbers. D is a synthesized attribute used in declarations to store declared variables. To solve this problem, we can begin by increment the line number using the non-terminal declarations, and at the same time, we store in the inherited attribute D prime the declared variables. At the bottom of the tree, we transmit the inherited attributes D prime and N prime to the synthesized attributes D and N, and we go from bottom to top in the tree. Next, we transfer the synthesized attributes D and N to the inherited attributes D prime and N prime of the non-terminal statements. We go from top to bottom in the tree. We increment the line number in the inherited attribute N prime, and the value of D prime is transferred down in the tree. Finally, we compute the synthesized attribute U and D. For each non-terminal statement, we put in the attribute U and D the variables that are not located in the set D prime with their line numbers. For production P1, we put N prime declarations equal 1, D prime declarations equal empty. At the top of the tree, we transfer the synthesized attributes N prime, D prime to N and D. The attribute U and D is in the non-terminal program is equal to the attribute U and D in statements. For production P2, we add the value of N prime by 1 and we put the inherited attribute D prime, the name of the variable. The synthesized attributes D and N are transferred from bottom to top. For production P3, the inherited attributes N prime and D prime are transferred to the synthesized attribute N and D. For production P4, the inherited attribute N prime is incremented by 1 to count the number of lines. The value of D prime is transferred from top to bottom. The synthesized attribute U and D is computed from bottom to top. We assign to the undeclared attribute U and D the name of the undeclared variable with the line number, which is not located in the attribute D prime. Let us now define the production of the grammar G DTD used to generate all DTDs. We define an unambiguous and non-left recursive grammar in order to be able to program it. The productions P0 and P1 define the syntax of a DTD. The production P2 and P3 define the element and the type of element. The production P4 to P7 produce the attribute declaration, the attribute type, and the attribute option. We use the non-terminal attribute suite to generate multi-attribute types and options. The productions P8 to P11 generate element type, which can be there's PC data, any empty, or a list of operators. The structure of an element type is a parenthesized expression with operators. The production P18 to P21 generate the terminal operator, which can be star, plus, or exclamation mark, or empty. The production P22 to P25 generate the attribute type, which can be cdata, ID, IDREF, and enumerate. The productions P26 to P28 generate the character string enumerate. The production P29 to P31 generate the attribute options that can be dièse fixed, dièse required, dièse implied. The production P32 and P33 generate the initial value for attribute options. For a given DTD, we can implement the following derivation tree. The production P0 generates the non-terminal DTD. The production P1 generates the identifier for the document, and the production P2 generates the element A. The productions P16 and P17 generate B. The production P17 generates C. The production P1 generates the element B, and the production P10 generates the PC data. The production P1 generates the element C, and the production P10 generates the PC data. To compute the semantic equation, we can divide the production of the grammar G DTD into three groups. The group 1 from production P0 to P11, group 2 from production P12 to P17, group 3 from production P18 to production 33. The production of group 1 and group 3 reproduce the attribute D of the given DTD that are outside the inner parentheses. Then, if we have the following DTD, we conserve the outer parentheses and our program didn't remove the inner parentheses. The production P11 generates the outer parenthesis in the declaration of an element and initializes the preceding operator of the inner list to the empty string. The production P12 and P13 do the same as the production P11 in terms of attributes. We define in the production P14, O list 2 is the operator of the inner list list 2, O1 list 0 is the operator preceding the inner list list 2. If O list 2 is equal O1 list 0 is equal and we eliminate the parenthesis in D list 0 as we regenerate the parenthesis in D list 0. Production P0 and P1 define the syntax of a DTD and reproduce in the attribute T of the given DTD that are outside the inner parenthesis. The production P2 and P3 reproduce in the attribute D of the given DTD and define an element and the type of an element. The productions P4 and P5 reproduce in the attribute D of the given DTD and define the attribute declarations and attribute options. P6 and P7 reproduce in the attribute D of the given DTD and define the attribute options. The productions P8 to P10 reproduce in the attribute D the element type which can be empty any or DS PC data. The production P11 reproduce in the attribute D a list of operators and initialize O1 of list 2 to empty. The production P12 reproduce in D the structure of an element type and initialize O1 of list 4 to AND logic if the preceding operator O1 list 0 is empty or equal to logic AND. The production P13 reproduce in D the structure of an element type and do the same as the production P12 for O1 using the operator OR. The production P14 does the same as the production P12 for the operator O1 and reproduces in D the structure of an element type by removing parentheses if O1 list 0 is equal O list 2 and O list 2 is equal logic AND. The production P15 does the same as the production P14 for the operator OR. The production P16 initializes the previous operator O1 list 2 to empty and reproduce indeed the structure of an element type by removing parentheses if O1 list 0 is equal O list 2. The production P17 produces indeed the identifier of a type element, and the productions P18 and P19 generate indeed the operators star and exclamation mark. The productions P20, P21, and P22 produce indeed the operators plus C data and empty string. The production P23, P24, and P25 produce indeed the attributes of elements which are ID, IDREF, and enumerate. The production P26, P27, and P28 produce indeed the element attribute enumerate. Productions P29, P30, and P31 produce indeed the attribute options for an element which are dièse fixed with initial value, dièse required, and dièse implied. The productions P32 and P33 produce indeed the initial value for the attribute option dièse fixed. Let's now speak about our experimental result. We have implemented the function eval. This function is a switch statement in which there is one case for each production in the grammar G DTD. In fact, we have a pointer to the node for each production. If the production, as example, is a PK, then for each children of the node, we can compute the inherited attribute of the children by the semantic equation of the production PK. We can call the function eval for each children of the node, and we then finally we can compute the synthesized attribute for the node by the equation of the production PK. The developed program takes a DTD as input and produces a DTD as output by calculating the structure of an element and by removing uses parentheses. As example, for the following DTD, we remove the uses parenthesis from line 2 for the element A. We remove the uses parenthesis in B and C, and we remove the element parenthesis for the element C for E and F. Then we obtain the following output. Speak about our conclusion and perspectives. In this paper, we created a new formal framework for the set of DTDs in the form of context-free language. We created a context-free grammar for the set of DTDs. We enriched the context-free grammar G DTD with attributes for eliminating the unnecessary parentheses in the declaration in the DTD. We can rewrite the source DTD into XML document for an intermediate model while retaining the DTD declarations. Our contribution is that in the case of multiple transformation, we can convert the DTD to another intermediate model such as XML and apply the style sheet to the intermediate model for each transformation without having to analyze the source DTD. In the future, we will also explore a way to map DTD to relational schemas and use traditional relational database engines to process XML documents, since XML is emerging as the data format of the internet and there is a need for storing and querying XML documents. Thank you for your attention.